Episode 4: Inorganic Color Pigments, Stability, Heat Resistance, and Their Limitations. In this episode, we focus on inorganic color pigments and understand why they are still extremely important in automotive coatings, even in an era dominated by high-chroma organic pigments. Inorganic pigments are often chosen not for brightness, but for reliability, stability, and long-term performance under harsh conditions. Inorganic color pigments are typically based on metal oxides, mixed metal oxides, sulfides, or other mineral-type structures. Their color originates from electronic transitions associated with metal ions, rather than from extended organic molecular systems. Because of this fundamental difference, inorganic pigments behave very differently from organic pigments in terms of stability, opacity, and durability. One of the biggest advantages of inorganic pigments is their exceptional thermal stability. Automotive coatings often undergo high-temperature baking during curing, especially in OEM processes. Inorganic pigments can easily withstand these temperatures without color change, decomposition, or loss of performance. This makes them ideal for primers, base coats, and functional layers that experience thermal stress. Light stability is another major strength. Inorganic pigments are generally very resistant to UV radiation. Their crystal structures are already in a low-energy, stable state, so they do not readily participate in photochemical reactions. This translates to excellent resistance to fading, chalking, and color shift over long-term outdoor exposure. Most inorganic pigments are also chemically inert. They show high resistance to solvents, acids, alkalis, and environmental contaminants. This chemical stability is particularly important in automotive applications where coatings are exposed to fuels, oils, road salts, detergents, and atmospheric pollutants. From an optical standpoint, inorganic pigments are usually more opaque than organic pigments. Their relatively high refractive index and larger particle size lead to stronger light scattering. This gives good hiding power, which is especially useful in solid colors and primers. However, this same opacity limits their ability to produce clean, bright, and transparent colors. Inorganic pigments typically produce muted, earthy, or dull shades. Reds tend to be brownish, yellows tend to be ochre or mustard-like, and blues and greens are often less saturated. This is a direct consequence of their electronic absorption mechanisms, which are broader and less selective than those of organic pigments. Particle size also plays an important role. Inorganic pigments generally have larger primary particle sizes compared to organic pigments. This makes them easier to disperse and more stable against flocculation, but it can also reduce gloss and smoothness if not properly balanced with the binder system. Automotive topcoats, especially high-gloss finishes, require careful control to prevent surface roughness. Density is another important characteristic. Inorganic pigments are usually much denser than organic pigments. This affects formulation calculations, sedimentation behavior, and storage stability. Because of their high density, inorganic pigments can settle more easily in liquid paints if rheology is not properly controlled. Some inorganic pigments also bring functional benefits beyond color. Certain oxides contribute to corrosion resistance, UV shielding, or infrared reflectivity. These multifunctional roles make inorganic pigments valuable in primers and functional coatings, not just decorative layers. However, inorganic pigments also have limitations. Their limited chroma makes them unsuitable for bright, vivid automotive colors on their own. This is why modern automotive color palettes rely heavily on organic pigments for visual impact, often supported by inorganic pigments to improve hiding and durability. Another limitation is regulatory pressure. Some traditional inorganic pigments contain heavy metals such as lead, chromium, or cadmium. Due to environmental and health concerns, these pigments are increasingly restricted or eliminated from automotive use. Modern inorganic pigments are designed to meet regulatory requirements while maintaining performance. In formulation practice, inorganic pigments are often used as part of a pigment blend. They may provide the base tone, opacity, and durability, while organic pigments fine-tune hue and chroma. The challenge for the formulator is to balance these components to achieve both visual appeal and long-term stability. In summary, inorganic color pigments are valued for their heat resistance, light stability, chemical inertness, and opacity. Their limitations in brightness and chroma mean they are rarely used alone in modern automotive topcoats, but their role remains critical in achieving durable, reliable coating systems. If you have any doubts about inorganic pigments, their selection, or how they are combined with other pigments in automotive formulations, leave your questions in the comments and let me know. If you're ready, the next episode will move into organic pigments, where we will explore why they deliver bright, clean colors and what challenges they bring to automotive coatings.